Hello, everybody. Good afternoon, or excuse me, I guess it's morning where you are. It's afternoon where I am. I happen to be in England right now, so we're doing this multinationally. This is going to be a big data overview. We're going to look at some natural language parsing, and the development process to produce some results with the HPCC platform, but most importantly, we're going to give you a broad overview of the platform. So let's get started here. If everybody's good, can everybody hear me? If so, just raise your hands in the WebEx, and I want to make sure that everybody's good to go and there's no problems. Taylor has raised his hand. Thank you, Taylor. Vinny has raised his hand. Good, good. Anybody else? That's good enough. I guess we've got a few people that can hear me, so we're going to get started here. So welcome, and what we're going to do is we're going to start with an overview of the platform and do some getting started stuff, showing you how to get things installed and get some data onto a VMware type of installation of HPCC, and how to define your data and get it ready to go. And then we'll be playing with some code that's going to be parsing some semi-structured data and parsing some unstructured data. And then we'll do some post-processing on those parse results. And that creating a delivery service we're not going to get to, I don't think, today, so I won't even talk about that. So the primary goals of this thing is so that you become familiar with the HPCC platform, the stuff that we have on there and available to you, get familiarity with the ECL programming tools and the enterprise control language itself, and the IDE and the ECL watch tools that we use when we're working with the language. You need to become familiar with the basic concepts and syntax of ECL, and we're going to talk at a fairly high level about our parsing technology. So all right, can you hear me now?
Yes.
Somebody talk back to me.
Sure.
There we go.
Yeah, I'm not sure what just happened, but now we can hear you.
Yeah, somehow my phone got disconnected from the call, so okay. I had to rejoin. At what point did I die?
It was just the last 2 minutes. So if you just maybe want to backtrack.
So let's go back here to the PowerPoint here, and did you hear everything about this, or did we hear everything about this?
I think you were just ending with that. Yeah.
Okay. So you're going to become familiar with the platform and the tools and the concepts and some parsing syntax, and we're going to start with a very quick demo, which now takes us into, here's some code. We've got some input data that I'm going to simply run a job. The environment that we're looking at right now is the ECL IDE. It's a standard Windows type of program, and I'm going to be hitting this submit button in a second here, and I'm going to be running this code, which is simply going to be outputting some records from this file and outputting some records from this result of working with that file. So what we're going to be looking at is the input data, and then we're going to look at the end of parsing some results. So when I hit the submit button, it runs the job. I've submitted this job. This is actually going from where I am in England to a training cluster that's in Boca Raton, Florida, and it's going to be recompiling this thing. It's compiling the job now, and it's running the job, and it's done. So what we're looking at here is the input data, which might be familiar to some people. The King James Bible is freely available on the internet. It is without cost to anybody, and so it makes very good demo data, especially as it's unstructured and allows us to do some nice parsing to that. So we're going. That's the input. That's the form of the data that we're going to be playing with, and the end result that we're going to be looking at is discovering from that the names of people and their relationships. For example, Abda is the son of Shammua, and that is in NE. What's NE? Anybody know? Nehemiah. Okay, 11:17, wherever that is. So I am not a Bible scholar, so I don't pretend to be able to understand or pronounce any of these names, and forgive me if I mispronounce them, please. So this is where we're going with all this. So let's talk now a very quick overview of the HPCC systems. Number one, why does it exist at all? And it was not created, it was not created with the idea that we wanted to sell this technology. These are tools that we developed simply because we needed them. And we developed them beginning back in 1999, and we were working with big data problems before the term big data had even been invented. So this is the end result of over 15 years of development on systems that are designed to solve the kind of data problems that we had originally, and the kind of data problems that have been brought to our attention by the external customers that have been using it for almost as long as we have. And now, for the last 5 years, we took it open source 5 years ago. For the last 5 years, we've been developing it along the lines of the kinds of input and the problems that we get from the community. So we created only to solve all of our data handling problems as we were developing our data products. So this is a platform that began its life for the first 10 years or so as a proprietary platform and has been now open source for the last 5 years so that we can share this technology with everybody in the world. And the result of that is what we have is a single, fully integrated platform that supports the entire life cycle of big data product development. What that means, basically, is that if you're familiar with Hadoop, we're a little different from Hadoop, because my understanding of Hadoop is that it began when Google produced its MapReduce paper. I believe that was in 2004, and somebody started the Hadoop open source project, I believe, in early 2005. If I'm wrong about those dates, please correct me later, but that's what I believe is the case. And being an open source platform from day one of the issues around Hadoop for operational installations is the fact that there are a lot of add-on products that have been created separately and independently from the core open source. Some of them are open source and some are not, but in order to create a full and complete operational installation, you pretty much need to have a laundry list of add-on products in addition to the core Hadoop code itself. And that's one way where we are very different from Hadoop, because we have always been a single, fully integrated platform that's been designed by the same team of people and as an integrated platform for the whole thing. It supports our raw data ingest and our data transformations to product. These are both accomplished on our Thor clusters. Thor clusters are sort of equivalent to a Hadoop cluster. And we also do our end-user query development, and we've got a cluster type that we call Roxie that is designed to handle our end-user query delivery. So Roxie is our data delivery engine, and that's the front customer-facing portion of the system, whereas Thor is a back-office tool that is designed to work with huge amounts of data and get it all ready to go and turn it into product data from the beginning of the life cycle, where data comes in the door from wherever it comes from and transforms itself into the final product data that everybody can go ka-ching, ka-ching, ka-ching with. Okay? So the complete data value chain begins with collecting the data, be that structured, unstructured, or semi-structured data. We can deal with all of that stuff. And we ingest it by getting that data onto the HPCC platform and so that we can begin working with it. And the first thing we do when we begin working with any data that gets into the platform is we take a look at what is it, what do we got? That's our data discovery. Make sure that what we've got is reasonable data, that that there are not a lot of garbage in there, that when a vendor says there's a data value in the field, that field is actually populated with data and things like that. And then we do the standardized cleansing and standardization, where we clean up the data, make sure that things are formatted. For example, you know, we can get data from all sorts of sources, and I know of about 10 or 15 different ways that you could format a standard U.S. phone number. So one of the things we do is take those phone numbers in whatever form they happen to come into us as, and transform them into one standardized format that we can easily deal with in all of our products. We can also do our statistical analysis of that data as it comes in. And once we've got the data in and cleansed and standardized, then we can integrate it with all the existing data that we've already got in-house to add to it. We can link it, index, fuse the data together so that we know that John Smith that lives at 123 High Street and the John Smith at 456 Main Street that registered a car, that they happen to be the same guy because he just moved to 123 Main Street from High Street, and now we know that we can discover that from the linking and indexing and the data fusion steps that we do. We analyze that data. All the data that comes in our door forms a huge, I believe the current term now is data lake. Okay, it forms a huge lake of data, and we have the tools built in to the HPCC platform that allows us to do statistics and machine learning on that. We do have a machine learning library that is part of the infrastructure. And then, of course, our final data delivery step, we can obviously do batch processing, and once data is done, simply ship it out the door back to where it needs to go. But we've also got the Roxie cluster type, which is designed for thousands of concurrent queries to be handled in typically sub-second response for each one, so that we can actually agree to service level agreements where we produce millions and millions of query results per hour for any given customer that we need to. So it's querying, visualization of the data. We keep things redundant. We have enterprise class availability. Okay, so that's the complete big data value chain that we have implemented, all using the HPCC platform. The platform consists of infrastructure and two types of clusters. We have a data refinery. We call this Thor. Thor being the Norse god of thunder. He has a big hammer in his hand, and as I tell all my classes when I teach, the reason we call him Thor is because Thor's hammer will beat any big data problem into submission. It's designed to work with huge amounts of data. It processes every one of billions of records, and it creates billions of improved records. So I use as an example doing an inner join between a 10 billion record data set and another 10 billion record data set, which is not an uncommon thing for us to do. So that's the kind of thing that Thor does. Thor is the back office tool. It works with huge amounts of data and allows us to take all the data that we have and pre-process it to produce final results data for most of the pre-canned queries that we're going to give to the users. And we simply provide users with the queries that will allow them to say, okay, this time I'm looking for Tom Jones, and we send back the Tom Jones records. This time I'm looking for Susie Smith, and now you get the Susie Smith records. And since we've done all the work up front in Thor, that allows Roxie, the rapid data delivery engine, to search quickly for just those records that that particular customer needs at that instant, typically with a sub-second response for each query. It's a massively parallel processing data delivery engine, just like Thor is a massively parallel processing big data supercomputing technology platform. These two are tightly coupled with all the infrastructure. We have infrastructure items that make it all work together. We have distributed file utilities that allows us to keep track of all the data. We have enterprise service platforms that do our inter-process communication, and so they work both with Thor and Roxie, and it's tightly coupled with a single programming language, the ETL programming language, that we use to do our ETL work on Thor and our query development and query delivery on Roxie. So it's a single integrated environment so that once you've got a team of people trained on it, you don't need to have experts in a half a dozen different add-on tools in order to turn your data into a production operational installation. The hardware systems are just standard rack mount servers, which are composed of commercial off-the-shelf components, COTS hardware, standard servers that you or I can order up from Dell anytime. They go into our racks, and ideally those components are homogeneous. Back when we were a proprietary system, we made that homogeneous requirement a requirement. Now that we're open source, we can't make it a requirement, but it makes a lot of sense because the example I give in class all the time is there's an old adage that says a chain is only as strong as its weakest link, therefore a supercomputer is only as fast as its slowest node. So if all the nodes are exactly the same and you give them all exactly the same amount of work to do, things will get done in as fast a time as it's possible to do. They are basically just individual servers with CPUs, memory, and hard drives, and we network them all together to operate together as a massively parallel processing platform. Now, massively parallel processing means that the concept we use, the strategy we use to defeat the big data problem is divide and conquer. So it really comes down to dividing the data across all the nodes so that each node in the computer, in the supercomputer, does its fair share of work. One of our standard cluster sizes for Thor clusters is 400 nodes. So if each node gets approximately 1/400th of the data to do the work on, then things will go as fast as it's possible to do, and we get things done 400 times faster than it would possibly ever be able to be done on a single box. The nodes in these clusters are managed en masse instead of individually. That allows us to do coordinated processing, such like global storage. Now, what that means basically is that our Thor cluster was designed originally around solving an indexing problem. And the indexing problem that it was designed to solve was to build indexes. We were working, before we had the Thor cluster, we were working with massive amounts of data and hosting it on Sun EMC platforms. And it got to the point where our weekly index build for that platform would take 110 hours to run on a pair of 26-way suns. 110 hours is most of the week, so if anything happened in the middle, any problem, then we slipped our release date. So what we did was we decided that what we needed was a massively parallel processing ETL platform to do that, and that's when we decided to design and implement Thor. Our very first Thor cluster was 400 nodes. This was, my goodness, what year was it? About 2001 or so was our first Thor cluster. And the way, it might have been 2002, I could be wrong. But what it did was it allowed us to make that index job run a lot faster, because when you think about what it takes to build an index, if you've got a 10 billion record data set and you want to index that 10 billion record data set on last name, first name, you need to extract from your data set the last name, first name, and the record pointer to the record that that came from, and then you need to take those 10 billion leaf node entries for your index and sort them. And sorting 10 billion entries is what was taking the Sun 26 ways so long to do. So our Thor was designed from the very beginning to be a massively parallel sorting machine. It was designed to build those indexes for us so that once we had the leaf node entries in the index all properly sorted, then we could build the binary tree and finish off the index and have a properly done ISAM file index for the Sun EMC platform to work with to deliver our data. By the time we actually implemented our first Thor and put the data build, the index build into production, that index build went down from 110 hours to between 6 and 8 hours on our first 400 node Thor cluster. So that's the kind of improvement in processing that Thor gave us. And what that describes is the fact that a Thor cluster is a brute force machine. We're not trying to do anything fancy. We're not trying to do anything elegant. We're just trying to brute force a whole lot of data. And so it's designed to operate on massive amounts of data with billions of records. It is an open data model because the data model is defined by the user. Unlike Hadoop, we don't work with a key value paradigm. We work with standard index sequential access method files. In other words, flat files, CSV files, XML files. You can work with key value pairs if you want to, but you're not required to do that. So we have created this technology based on standard database type of concepts of files with records and fields in them, or tables and rows and columns if you prefer the SQL terminology. Either one. That's the open data model. It is scalable in that we can, if you have a problem in that you've got a 10-node cluster and you've got too much data to work on a 10-node cluster, go out and buy another 10 nodes, and now you're running on a 20-node cluster and things are going a lot faster. Okay? That's the whole point. I believe that the the theoretical limit to how many nodes we can put together before we see significant performance degradation is somewhere in the range of 10,000, and we don't do things like that. The largest clusters we've ever found to be necessary are 400 node clusters because of the improvements of hardware over the last 15 years have negated the need to go to more nodes than that. And we literally work with multiple petabytes a day on those 400 node clusters. For example, I happen to know that one of our data sets is 28 terabytes in size all by itself, and we use that data set to bang against other data sets that are almost or equally as large. So that's the scalability. You can scale up to actually meet your needs or scale down. If you only need 4 nodes, you only need to buy 4 nodes. If you need 400 nodes, well then it's going to work. It's truly parallel in that what we're doing is divide and conquer across all the nodes by how we divide the data. That means that the jobs that are running on a 400-node cluster are determined by a single .so. In other words, the same object code is running on each of the nodes, and the work is done, the same work is done on every single node, and data is swapped between the nodes only when and as necessary. We've got a very powerful optimizer because the ECL language is not executable. It's a declarative language. Therefore, the way that the optimizer works is your ECL code defines what it is that you want to happen, and the code generator optimizer compiler part is going to interpret from what you've just defined in your ECL code as to exactly how that needs to happen, and it will generate a very efficient C++ code, which is then compiled into standard .sos that run on each individual node of the cluster. So this optimizing compiler utilizes all the very best techniques to make things go as fast as possible. That's the Roxie cluster now. Is a little different from a Thor cluster, because a Thor cluster does one job at a time with massive amounts of data, whereas Roxies are a massively parallel processing system designed to handle thousands of concurrent queries. It's low latency. That means that these queries typically complete in less than a second. It's not unusual for that to be like a tenth of a second or a quarter of a second. It all depends on the complexity of the query itself and how much data it has to access to answer any given individual query. It is not a key value store. As I said, we don't do that. We don't do key value data stores. We do standard data files. Fuzzy matching, multi-key retrieval, complex queries, standard database type of concepts. Roxies are designed to be highly available. Our standard production Thor is 400 nodes. Our standard production Roxie is 100 nodes. That means that a single 100-node Roxie can handle, given that that we have multi-threading on the operating system, and we can handle 30 or 40 threads at least on each individual Roxie node. That means a 100-node Roxie cluster, given 40 threads, can do 4,000 concurrent queries, and if each query occupies about a quarter of a second in time for the results, that means that 4,000 times a quarter of a second is, of course, going to be about 16,000 queries per second on a single 100-node Roxie, but our production environments typically pair the Roxies so that you've got a pair of Roxies operating at the same time on the same queries, delivering the same kind of results to all the users. So instead of 16,000, you're getting 32,000. And let us not forget about the disaster recovery site that is just waiting out there with a couple more of these things should we need to fail over. So the high availability is exactly what Roxie is all about. It's designed to be massively parallel. Every node in every Roxie can service any query that comes into that individual Roxie. Whatever that Roxie is designed to service, what kind of queries, every single node can handle that. So if a drive goes down, you've got data redundancy in there. If a node goes down, we've got node redundancy in there. If a whole cluster goes down, we got another cluster sitting beside it. And if you can't get to our production facility, it fails over to disaster recovery. So we are designed for high availability, 24/7, 365. And once again, if a 100-node Roxie isn't getting you where the SLA that you need, then you can scale this thing, just like Thor, highly concurrent, thousands of concurrent clients simultaneously executing their queries on the same Roxie system. Shared nothing is the architecture, so there's no single point of failure on a Roxie cluster. Extreme fault tolerance. So the platform itself, the environments all the components are part of the open source environment. In other words, our community system open source environment includes everything that you need to actually go into production. We have been informed after the fact from people, from companies, external companies, that they have gone into production with HPCC Systems without ever even talking to us about it, other than maybe asking a few questions on our community forums. So everything that's necessary is there. We've been doing this, we've been developing this system since 1999, which is a few years before the other guys started doing their thing. Very few moving parts means that there's an integrated solution. The whole system is designed to work together through the entire data life cycle. The data is meant to be coming in from the outside. It's meant to go onto Thor. Thor is designed to do all of the extract, transform, and load data ingest process that you need to do. It's designed to do your data query development for your Roxie and your final product data development. And then all you need to do at the end of all that development is publish your queries to Roxie and let users start hitting it, and bam, you're going ka-ching, 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 which is exactly what you want to do. Multiple data formats. We support fixed and variable length format files, delimited records, XML. What's missing from this slide is we now support JSON also, so that's in there. The one language that we're using means that both environments, the query publication and the data munging, is from the same set of tools. So all you need is one set of people trained in one technology instead of multiple technologies as you do with some other systems. So ECL, once you have people that know ECL, they can work on data munging, they can work on query development, whatever it is that you have a need for. It's consistent tools between the whole platform also. This is the advantage of having a single development team guide and deliver this thing for the first 10 years of its life. You know, only now as it's open source are we beginning to get some more input from other people, and there's enough here already that all the input are usually pretty good ideas. What a good idea to add. Data. It's an open data model. We're using standard files and fields. It is fairly simple because it's the standard database concepts that we all learned when we took Database 101. You know, you got a table, and in that table you got rows of data, and in those rows there are columns. Or if you want to use files with records and fields, all those synonyms work. It's exactly the same thing. You can compress, you can express exactly what you need to do to work with your data easily. We've got a lot of ECL primitives that are designed specifically to work with your data. And it's implicitly parallel. All of the data in our system is implicitly parallel. It is always distributed data sets, but at the level of the ECL programmer, the infrastructure in the middleware, specifically the distributed file utility, is designed to keep track of data, where's all the data, so that the ECL programmer doesn't have to. Just like the infrastructure of the code generator is designed to handle the complexities of massively parallel execution, so that the ECL programmer only needs to work at the level of solving the data problem with a single logical file on a single logical cluster. You don't need to worry about whether am I running on a 10-node cluster this time, or is it a 100-node cluster. Your ECL code is exactly the same for both the data and the code. We typically use ISAM files, native support for flat files with fixed or variable length records. Now that's internally the way we want to work, because that makes things very, very accessible. As far as getting data from the outside world, we can take data in from any format. But we can work with CSV type of files with any kind of delimiters. We can work with XML and JSON data sets, all of that. Native support, it works, and it just works. The one big difference between HPCC and, excuse me, I put in too many C's, didn't I? Look out. I'm getting too excited here. I'm having too much fun. So one big difference between Hadoop and HPCC is that the key value store paradigm that's used on Hadoop means that you can express the concept of a record, and that record might span multiple nodes. And that you don't get to do that in an HPCC cluster, okay? So one of the requirements that we have is that a single record is always holding complete on a single node. It keeps things simple. That means the file parts, the physical file parts on each node of the cluster that comprise one part of a multi-part logical file that you're working with for your distributed data, that subpart, that single file part, is always a set of whole and complete records. Makes it easy to work with. You can have as many fields as you need to in your data. We use indexes. We have a fairly complex set of index rules. They are always LZW compressed. You can have standard search term indexes where you are simply loading on in your leaf nodes of your index the search terms and the record pointer to go get the record, but we don't usually use that anymore because things go faster when we replace that record pointer with the payload fields that are in addition to the search terms. What that does is it eliminates at least one disk I/O operation, disk I/O being the slowest thing in computing. We want to make sure that we eliminate as much of that as possible, and so the concept of payload indexes is a very powerful one that it helps keep our Roxie queries going faster and faster than is possible. So what is ECL? Excuse me one second. Okay, ECL. It stands for Enterprise Control Language, and if you do a Google search on that, ECL, you'll find that there are several ECLs out there, and only one of them is us. So ECL is a declarative programming language. In other words, you define what things are. You define what you want to do, not how to get it accomplished. Okay, you declare what things are. So the bottom line is that when you're writing ECL code, you're never really writing executable code. You're simply defining what computations need to happen and what results you want to see and how it gets done. That's the compiler's job. That's the job of the compiler, to parse through your ECL code, understand exactly what you need, and it then decides how to get the job done. It's a very powerful, terse, and expressive programming language. Unlike Java, high-level primitives such as join, transform, project, sort, distribute are available. Higher-level code means fewer programmers and shorter time to deliver complete projects. Okay, let me tell you a true story from a couple of years ago, since it this part of the slide mentions Java. Several years ago, I believe it was a company called SGI published a benchmark, and they ran what's called a TerraSort benchmark on a Hadoop cluster that they had just gotten with brand new hardware. They had 20 new hardware nodes, and they wrote this TerraSort clustering, and they published the results as a world record on how they did it. And what they did was they used 20 hardware nodes. Their results were about a minute 38 seconds, and it took 700 lines of Java to do this TerraSort benchmark. Well, when they published that, this was like a couple of days after they did it, they published it, we saw that, and we just happened to have taken shipment of exactly the same hardware that they had used in that. So we decided we were going to try it ourselves in HPCC. So we ramped up an HPCC cluster to do exactly the same amount of TerraSort benchmarks that they did. And here's the distinction between what we did. Number one, they did it in a minute 38 seconds. We did it in 25% faster. I don't remember exactly how many seconds it was. So it was 25% faster. They wrote 700 lines of Java to do their job. It took 3 lines of ECL code to do the same thing. And whereas they ran on a 20-node cluster, we ran it on exactly the same hardware, but on only a 4-node cluster. So I think that's the definition of better, faster, cheaper. The language is extensible. As you create new definitions, they become primitives that other programmers can use. We also allow you to extend the language. If you have data types that we don't natively support that come in as your data, you can create those alien data types. You can also create plug-in library functions that extend the language. If you need to write a function in C or C++ or something like that, you can do that and add it in as additional primitives to the language. And we also allow you to extend the language by piping to command line programs. We have input pipes, output pipes, and through pipes. So the language itself is easily extensible. And of course, anything that's in there that you would like to see that's not there, you can simply submit a Jira ticket, or since it's open source, you can jump in there and add it yourself and submit it to GitHub, and we'll see how well that goes. The language is implicitly parallel. In other words, you write your ECL code solving your logical problem, treating the cluster as if it were a single supercomputer, and it is the compiler's job to handle all the problems of massively parallel execution on each of the nodes separately. So you don't need to be concerned with it. Just like the distributed data is automatically handled for you by the distributed file utility, the implicit parallelism of the code that's generated for you by the compiler means you don't have to think about it. It is a very high-level programming language. It is very terse and very expressive. So that means you get a lot of work done with very little code. There are no side effects, and definition encapsulation provides distinct, reliable, and easier to troubleshoot code. Okay. And the language is complete, from soup to nuts. Unlike Pig and Hive, ECL provides a complete programming paradigm. The interesting thing about ECL also is that it is a language that is designed purely, simply, and only for data manipulation. There's absolutely no GUI aspect to the language. So whatever your favorite GUI language is, be that Java or VB or C#, you can continue using that to develop your GUIs. You only need ECL on the HPCC platform. It's homogeneous, one language that expresses data algorithms across the entire platform, data ETL and delivery. So we are up to the point now where what we want to do is install this stuff. Oh my goodness, I've been talking a long time. So I'm going to go very quickly through this. These slides, you've got your own, you can get your own copy of these slides. So the installation of VirtualBox and the IDE is going to help you. You can run your VM player to run this stuff. Open the browser and do all these things. This is actually a step-by-step tutorial to do things like spraying the files, which I have already done, acquiring the data. The spray is the verb that we use to get data from the staging area called the landing zone into your Thor cluster and defining those files. Now we can go and look at some files that have been defined. I've got a couple of files here. Here's some ECL code that defines the record structure for an actress's file that came from IMDb. And it's got a single field in there that's a variable length string. It's called line. So that when and my file itself is a data set. It is a CSV file, which has got no separators and no quotes. So it's just variable length records that I have a comma, a carriage return line feed record delimiter. And then if we want to run this code, we can simply say, I want to output some records from that file. And I'm going to call that name input data. And here is the kind of data that we see in that file. And how many records are there? Where it is? Okay, good. There are 7,434,000 records in there. That's the actresses file. We did that. We've got also that King James Version file. Here's the definition of that data set. Once again, this is a record structure, a single variable length field called string called verse. And this is once again a CSV file, variable length record file. And when I want to see what the input data for that is, I can simply submit that and see the result. And that looks like what we looked at before. So, natural language parsing. Let's parse the actress. Parsing patterns are defined like this, looking like that patterns, so that we can use the parse verb to parse using the name pattern to find a name that's letters, commas, things like that. And we parse that guy, and we end up getting the names extracted from that original file. The same thing for the parse, the King James Version of text, is we're going to be parsing that stuff. We've got patterns in there that's going to parse through there, and it's going to be looking for those relationships. So it's looking for names that begin with capital letters and continue with all those other things. And we've got a progeny rule, which is the rule that we're looking for. And this is going to output the fact that we found Abda is the son of Shammua, etc. I think I will just stop at that point and open it up for any questions, since we've only got about 5 more minutes left in our hour.
Okay, thank you, Richard. Does anybody on the line have a question?
Is anybody still awake?
Be sure to unmute your line if you have.
Yeah, it's frustrating to talk without being heard. Let me ask if any of the folks here in the room with me have any questions. Any questions on any of this stuff? No, we haven't talked about Parse yet. No, that's part of the reason why I wanted you guys to come in here. So obviously, Trish, next time we need to do this for 2 hours, right?
Right.
I have a quick question.
Yeah.
Oh, please.
So we talked about the platform and how it's complete and how everything's in there, which is fantastic. Could you spend a moment and talk about the integration with other platforms? So say I'm already using a different platform like Tableau or something else. How's the integration?
Well, it depends on what kind of integration you want to do. The question was, how do we integrate with other platforms like Tableau and Hadoop and things like that? It depends on what kind of integration you want to do. If you want to pass data back and forth between the two, then it's a simple matter of outputting the data from the other platform and spraying it, working with it in HPCC, and then despraying that and passing back the results of the other platform. If you want to work directly with those files, I know that we've done some things where we put HPCC clusters right in parallel with Hadoop clusters, and we have a interface piece that allows the HPCC platform to read and write Hadoop files and do that seamlessly. And we also have a JDBC driver and an ODBC driver that allows like business intelligence tools to integrate with our HPC platform as the data server. Does that answer the question?
Absolutely, thank you.
Yep. By the way, I'm sure there are things that I should know about and don't know about, and so I have missed out saying.
So, Richard, maybe what would be the best way for someone new to the platform to get started?
Ooh, the best way to get started would be, number one, you've got the directions on here, and for the same kind of code that I was trying to show you here. To take a look at this code and download the VM and put it on your laptop or your PC and just start playing around with it. That's one way to do that. And an additional way to do that is once you've begun playing with it, we have online e-learning courses that are designed to teach you all the ins and outs of working with ECL. The first couple of them are free to everybody in the entire world. And for academic institutions, all you got to do is ask Trish nicely, and she will give you discount codes for all the rest of them that we nominally charge money for.
Okay. On the WebEx, I see that Vidi has raising his hand, has a question.
Okay.
Go ahead, Vidi.
No, this is I raised hand earlier, so this is
sorry
not for the question. Yeah, no problem.
Okay. Okay, does anybody else have a question for Richard? No?
Well, did I pass the audition?
You got the job.
Yay, team.
Okay, so as Richard had said, I want to add that any attendees on the call from Northeastern University will receive a complimentary voucher to take our online training. And as he said, these will give you the basics of learning ECL and the components of the HPC Systems platform that Richard discussed. And upon finishing the required introductory courses, I'll give you guys a promo code to continue on and take the advanced courses, which go into a deeper dive of what's under the hood and some advanced lessons.
And let me add one more.
Oh, go ahead, Richard. Yep.
Oh, let me add one more thing to the advice for what to do next is the HPCCsystems.com portal is your best friend because there are dozens and dozens and dozens of white papers out there talking about all sorts of things in regards to the kinds of specific things that might interest you.
Yes, that's a good segue of what I was going to state. As mentioned earlier, this webinar will be available for future playback and posted on our website at hpccsystems.com. So as Richard was saying, we encourage you to visit the site, register yourself, join our community to keep informed on upcoming events, platform updates, and other news. And with that, we are 1 minute from 12 o'clock noon Eastern Time, so this will conclude our webinar, and thank you again for participating, and have a great day.
Thank you.
Okay, thank you, Richard.